In this video, we'll talk about sigma notation as a way to make it easier to write very long sums, which can be useful for finding areas under curves. The sums we had to write for finding areas under curves were long and complicated. There were a lot of different terms. You had to multiply the height times the width a bunch of times over and over again, and that's kind of annoying. But we have a notation that makes it a lot easier to write these sums, to know what's going on, and to sort of see how they work without having to write all that out all at once. Our notation is the following. If I have numbers a1 through an, and we use a capital N here, then I can write the sum a1 plus a2 plus all the way up to an instead as a sum with a big capital sigma from index k equals 1 up to capital N of ak. And that's just how we define this notation here. It basically says, take the sum, that's what the sigma stands for, start the sum at k equals 1, where k is my variable in here, and go up to n and just add up every term along the way. So you generally read this as the sum from k equals 1 up to n of a k or a sub k, if you want to use a different notation for that part of the sum. Now for this notation, we have the sum sign. This just tells us that we're doing a sum here. We have our index, which is k. That tells us what letter we're using to mark what point we're at in the sum. We have our lower and upper limits of summation. And then we have our general term in here. The point is, as I go, I'm going to say, let k equal 1. Now let me put k into this expression, see what I get, and that's the first term of the sum. Then do it for k equals 2, do it for k equals 3, and so on until I get to n. Do it for n, and then stop. Now, the points here to keep in mind, the index always goes up by 1 every time, and it can start and stop at any numbers. Let's do some examples with this. I want to write the following 3 sums in summation notation, or sigma notation. You'll hear both words used to refer to the same thing. So, 1 plus 2 plus 3 plus 4 plus 5 plus 6. So this tells me, in general, I want to write a sum, and basically for every k, I just want to add the value of k, because if I write, say, k from 1 to 6 of k, what's that going to do? Well, for the first term, I am looking at k. I set k to 1, that gives me 1. For the second term, k is going to be 2, so putting that in gives me 2, plus 3, plus 4, plus 5, plus 6, so I get the actual sum I'm looking for this way. Now for the second one, how am I going to do this? The issue here on this one is that the terms are stepping up by 2 every time, not 1, but because I'm doing a summation, that always has to step up by 1. So I can get this one this way. I'm adding from 1. How do I get my first term? My first term is going to be 2 times 1. And this will do the right thing, because I'm stepping by 2 every time. That's where this coefficient of 2 comes into play. And where do I stop? Well, I stop when k gets to 4, because when k gets to 4, I will hit 8 for my last term. This will give me 2, 4, 6, 8. These patterns can be hard to spot sometimes, but it's good practice to get used to how they work. What about this last one? 1 plus 4 plus 9 plus 16 plus 25 plus 36 plus 49 plus 64 plus 81. What's the pattern here? Well, the pattern here is these are all perfect squares. So it's 1 squared plus 2 squared plus 3 squared plus 4 squared and so on. Now how do I write that in a sum? Well, I want to start from 1 and go up to 9, and at each step I want to add that number squared. This will give me 1 plus 2 squared is 4, plus 3 squared is 3, up to plus 9 squared is 81, and then stop. So this gives me the summation that I had here, written out in the sum form. And you can see it's much easier to write this guy out than it is to write the big one above. What about going the other way? This might be the more important thing to think about here. How do I convert a summation symbol into something I actually write out? So I from 1 to 4 of I, again, you can use any letter you want for the index as well. So you can use any letter, you can start any number, all these things can change depending on your problem. So I from 1 to 4 of I, well, this is going to be first level plug in 1, I get 1, second spot plug in 2, I get 2, third spot plug in 3, and fourth spot plug in 4. That's what I get there. Next one, sum from j equals 2 to 5 of j cubed. So for this one, I just want to start at 2 and step up till I hit 5 and write the cube of each one. So I'm going to get here, first term is j equals 2, so a 2 cubed. Second term is j equals 3, so a 3 cubed. Third term is 4, so a 4 cubed. Fourth term is 5, so a 5 cubed. Right? The numbers here don't tell me how many terms I have, they tell me where I start and where I stop. So I start at 2 and I stop when I hit 5. So 8 plus 27 plus 64 plus 125. For this last one, we have k from 0 to 3 of k squared plus 1. Again, any index is fine, any starting point is fine. I can just now plug these in. So I'm going to get 0 squared plus 1 plus 1 squared plus 1 plus 2 squared plus 1 plus 3 squared plus 1. I can solve it from there. I get 1 plus 2 plus 5 plus 10. That's how summation notation is defined, and how you can use it to help simplify or expand out different sums, which will see will make it easier to write out these summations for finding approximate areas under curves with this notation.